Good evening again. It hardly seems like 5 minutes I was last here talking to you. Okay, this time it's the science of Santa. You can see I'm getting serious now. I'm asking the question, as there's no children in the audience, is Santa compatible with the laws of physics? I'm a physicist and I've got nieces and nephews. And I was interested when they asked about Santa and whether he existed or not. I didn't want to lie to them, so I thought I better find out whether or not he might exist. So one way I thought of it was, well, okay, let's try and figure out how many laws of physics Santa actually breaks, and that will give us an indication. So we know that Santa is, at least allegedly, a rather portly, jolly fellow with a large white beard and a penchant for wearing red suits. But just because he has questionable fashion sense, that does not mean that he doesn't exist. What about the claims that are made about this fellow regarding what happens on Christmas Eve and early Christmas morning? And in particular, can we actually deal with any of the science that I've covered in other talks to try and address this particular issue of the feats that he's allegedly carrying out? He allegedly visits all households on Christmas Eve to deliver presents to all qualifying children. And how do they qualify? Well, it's defined by the naughty nice list, of course. So that is the statement that we're going to sort of look at. Can we reconcile it with any either science that we understand, or in particular, any science that I have covered in, this is a small selection of the talks I give. I've got about 40, 45 talks, mostly scientific. And I'm going to borrow some slides and some ideas from these talks in order to address them to the concept of science of Santa. So the particular sentence that we're going to pick apart is this one. Santa visits households on Christmas Eve to deliver presents to children. And we are going to treat it scientifically, so we're going to take it one bit at a time and say, okay, does he break any laws of physics for any of these aspects of his alleged feats? Let's just make sure we know what we're talking about first. We're delivering presents to children. How many children are involved in this particular feat? Well, we can approximate, and it has to be an approximation because it's very difficult to count them all. We know the Earth's population is about 8 billion. We know 25% or thereabouts are children. And let's just assume that half of them are eligible. Let's assume that Santa is quite generous and he will deliver presents to children even if they're not in Christian households. So that means he has to deliver about 1 billion presents. That, of course, assumes that the naughty nice list is naughty 0 and nice 100%. Now, any parents or grandparents in the audience might question that particular split, but let's just assume that to make the numbers easy. 1 billion children is what we're talking about. Okay, so we've got 1 billion children and Santa visits them. Okay, how does he get around? What's his mode of transport? He works in a sleigh pulled by flying reindeer. So, question 1, can reindeer fly? Well, we know that insects fly, and we know that birds fly, and we know that pterosaurs fly, though we don't see many of them these days. And of course, even some mammals will fly as well. Now, if reindeers can fly, well, they choose not to do so for most of the time, especially when people have got cameras out. There is very little evidence, and remember, physicists and scientists rely on evidence, not hearsay, not anecdotes. We need evidence. So there's very little evidence for reindeers being able to fly. But absence of evidence is not evidence of absence. Any scientist can tell you that. So just because we don't have any photographs of flying reindeer doesn't mean they can't. It just means when they decide to do so, no one's around and no one's got a camera. Same principle as UFOs, basically. Okay, so the jury is still out on that. How fast would Santa have to go if he's going to deliver 1 billion presents in one night? Well, you can calculate, assuming he spends very little time at each destination, he would have to travel at 2,000 kilometers per second. Now, that's fast. Yes, I admit that's fast. but it doesn't break any laws of physics, because we know from other talks that the fundamental speed limit in the universe is the speed of light. Fiat Lux is a series of talks I give about the nature of light. And Santa would only have to move at less than 1% of the speed of light, because 2,000 kilometers per second is only 0.007 of c, c being an abbreviation for the speed of light. So at moving no more than 1% at the speed of light, Santa is not breaking any rules, no laws. No object can travel faster than light can travel in a vacuum. Space, the universe is expanding. Space is actually stretching faster than that, but that's a different thing. So we're okay as far as how fast Santa has to move. But if he moves really fast through the atmosphere, aren't we going to end up with roast reindeer? Because we know that fast things traveling through the atmosphere, like for instance we mentioned meteors in the previous talk, we know that if a meteor or an asteroid comes into the Earth's atmosphere traveling at speed, it compresses the air in front of it and the air gets hot, and hence the object gets hot. This is something I cover in another talk talking about how stars work. And stars get hot because when you compress a gas in a large cloud and collapse it under gravity to form a star, that's why stars get hot, and ultimately they then use nuclear fusion to stay hot. But compression of gas produces heat. Anybody who's pumped up a bicycle tire knows that when you compress things, they get hot. So shouldn't the sleigh, and indeed the reindeer, moving fast through the Earth's atmosphere, heat up? Even if the sleigh is aerodynamic, surely it'll still heat up. And we know that anything that heats up, compression produces heat, anything that gets hot glows if it gets hot enough. We are emitting infrared light, but if we were to heat up, we would start emitting visible light. So isn't that a problem? Wouldn't you expect the sleigh moving at that speed to be a white, hot point of light in the sky? Well, maybe it was. Now, saying that Santa's sleigh is actually responsible for the Star of Bethlehem is getting things slightly out of kilter. But you could say that although it might not have been the Star of Bethlehem, bright lights in the sky, we see them all the time. I mean, I got a talk on UFOs where people are convinced that they see UFOs, not necessarily just on Christmas Eve. But there is a substance in the universe we know about, such that when you heat it up, it doesn't glow. Most things we understand, virtually everything in this room, everything outside the windows, everything on planet Earth, if you heat it up enough, it glows. But there is a substance that we know about, it's called dark matter. The universe is full of stuff like us, made of atoms, which are made of nuclei and electrons and other particles. But we also know, as of the last few decades, we have found the evidence that there is stuff out there that doesn't behave the same way as ordinary matter. We call it dark matter because we don't really know what it is, and that's just a label of our ignorance rather than anything else. But we know dark matter exists, and we know that when you heat it up, it doesn't glow. So maybe Santa and his sleigh are made of dark matter. That seems perfectly reasonable. Dark matter doesn't emit light. Also, dark matter doesn't absorb light or scatter light or reflect light, which means if the sleigh is caught in a radar beam, well, there would be no radar reflection. So that's why he doesn't show up on radar either. Okay. Right, so we've got 1 billion children and we're visiting what? We're visiting households. Okay, so Santa is visiting perhaps less than 1 billion households to deliver the presents. How does he get down the chimneys? He's a portly, jolly fellow, and therefore he's substantially more rotund than most chimneys, which are only sort of yo-big. So how can Santa possibly get down a chimney? He would have to be able to go down the chimney really fast, like 3,000 chimneys a second or something. Not impossible, but with his girth, he wouldn't be able to manage that. Okay. There are laws of physics that allow us to get around this problem because we know that presumably Santa, if he's made of atoms, maybe he's made of dark matter, but if he is made of atoms, we know atoms have a particular size and we know there's lots of atoms in us. But if you, according to the rules of quantum theory, which is talking about the laws of physics on the very small scale. We know that atoms are made of a nucleus and an electrons buzzing round. If you replace the electrons with another fundamental particle called a muon, it's like a cousin of the electron, but much heavier. If you replace the electrons with muons, the atoms will be much smaller by a factor of about 200. So instead of being a fellow of somewhat less than 2 meters height, if you replaced all of the electrons in his atoms with muons, which is perfectly possible, I don't know how you do it, but it's perfectly possible, then you end up with atoms that are 200 times smaller, and Santa would be about 1 centimeter tall. And he would drop down a chimney, no problem whatsoever. Now, I'm saying this is possible. I don't know how to do it, but just because I don't know how to do it doesn't mean Santa is breaking any laws of physics. So maybe that's what he does. But you say, yeah, but who has a chimney these days? Surely there's lots of domiciles in which you don't have easy access down a chimney. So how does Santa gain access to the house? Well, quantum theory comes to our rescue yet again, because when we look at how the world works when we're dealing with atoms and molecules, for instance, we find the rather bizarre situation that it's possible to actually go through solid objects. One solid object can pass through another. We're not used to it, because for most of us, solid objects are impenetrable. But when you look on the very small scale, it is possible for solid objects to pass through each other. Atoms are made of stuff in which the nucleus and the electrons are tiny compared to the amount of space occupied by an atom. So as far as the laws of physics are concerned, yes, you can pass through. And therefore, it's a process called tunneling. Therefore, Santa can tunnel from the outside of a house to the inside of a house without ever having an open door or an open window. We've seen it happening. We know it happens. There is documentary evidence. There are microscopes built on this principle that it is possible to go through solid objects. And yet, we don't normally see it for large-scale objects, but maybe Santa has figured out a way of getting the quantum world to exist in his world, or if you like, vice versa. So this concept of tunneling is a phenomena that we know about. Maybe Santa has mastered it. Okay, so he visits households. What does he do? He does this on Christmas Eve. Doesn't mean he's got a short night. Remember, if he does it in a correct time zone order and uses the rotation of the Earth to his advantage, he's actually got more than 24 hours to play with. So one night, yes, but one night if you use 24 time zones means that you actually have about 36 hours to play with. Okay, so how, even if he's traveling at relativistic speeds, at close to the speed of light or a fraction of the speed of light, how does he manage to get all that done in only 36 hours? Well, we're relying on quantum theory a lot, doing a lot of the heavy lifting here. We know from quantum theory that, for instance, an atom or a molecule, let's imagine an atom that's rotating or spinning. It can spin clockwise and anti-clockwise at the same time. Now, normal objects that we see sitting on a table or whatever don't tend to do that. The Christmas ornaments at the back there seem to be either static or turning one way or the other. But atoms and molecules and things at the quantum scale can do two things at once. And in fact, they can be in two places at once. An electron can be here and there simultaneously. So if that's possible in the quantum world, and it's possible for atoms and it's possible for molecules, well, if Santa is made of molecules, why can't he be in two places at once? And why limit yourself to two? If he's not breaking any laws, why can't he be in 1,000 places at once or 1,000,000 places at once? As far as we know, that does not violate any laws of physics. We've never seen that happen before. Maybe Santa has figured that out. If, for some reason, you believe that you can't be in two places at once, you have to find a different way of visiting all of these many, many places in a short length of time. If you can't be everywhere at once, well, there is another alternative. And that is when we look on the larger scale at the way matter behaves and the way space behaves, we think of space as being empty, but in fact, space can be distorted or warped by the presence of matter. You perhaps know about or have heard about black holes, which are rather extreme objects with very strong gravity, which can distort and warp the space around them. In principle, any matter can distort the space around it. And maybe Santa has figured out a way of distorting space so that instead of having to visit each of these locations, he distorts space in such a way that all the locations come to him. And that saves a lot of time. So we don't quite know how he manages to do that, but we know that matter distorts space, and the distance between two objects will depend on how the matter is arranged. So maybe he's figured out a way of manipulating matter in such a way that the distances to all these places he has to visit are shrunk down to much shorter distances. If he does that, that's very clever. I haven't figured out how to do that myself. Okay, he's visiting households on Christmas Eve to deliver presents. Okay, we've got 1 billion children. How many presents are we delivering? Well, how could he carry them all? Let's, for the sake of argument, assume there's only one per child. Let's not assume they've got 36 presents each. Okay, so one relatively small present each. How can the sleigh hold Santa and 1 billion presents? Okay. The sleigh is only a few meters in size, but it's a few meters in size as we would measure it on the outside. It is possible for objects to be bigger on the inside than they are on the outside. And I'm sure you're thinking of Doctor Who and the TARDIS. Yeah. Wrong. No, we have evidence that black holes, for instance, are bigger on the inside than they are on the outside. So the TARDIS is a work of science fiction, but that doesn't mean you cannot have a volume which is bigger on the inside than the outside. So that is the case for black holes. Maybe it's true of other arrangements of matter that we haven't seen yet. Just because we haven't seen it doesn't mean it doesn't exist. We know that that is a possibility. So maybe Santa has figured out a way of making the sleigh bigger on the inside than the outside. So although it's only a few meters long, it's big enough internally to hold 1 billion presents. If you don't like that, there's another alternative, and that is we think there are 3 dimensions of space: forward, backward, left, right, up, down. But we are only aware of 3 dimensions of space. Some scientists believe there are more, but we simply cannot perceive them. We cannot access them. Some people believe there are actually 10 dimensions or 11 dimensions. The 3 we're familiar with and a whole load we can't access. But maybe Santa can. Maybe these 10 dimensions do exist, and all Santa has to do is to take the presents in 3 dimensions, shift them into another dimension, and then he's basically pushed them into invisibility as far as we're concerned. When he gets to his final destination, he pulls them out of that destination and puts them under the tree. Again, I don't know if that's the case. I don't know which of these 2 is most likely. The sleigh is bigger on the inside than the outside, or Santa uses extra dimensions. We have not ruled out the possibility of extra dimensions. The catch is we can't see them, but Santa, well, he's special, isn't he? Maybe he can. So again, he doesn't break any rules as far as we can tell. You might say, well, yeah, but you're stretching a point here because you're saying he doesn't actually break any rules, but surely the amount of energy that would be needed to do any of these things would be absolutely huge. The energy needed to take a sleigh and Santa and 1 billion presents and move them at high speed through the Earth's atmosphere, or to warp space in such a way that the distances shrink to allow him to visit all of these places. Yeah, that might be possible, but it would need huge amounts of energy. Okay, so we can turn this problem into, well, how does Santa access all this energy? Well, we know that a black hole can power a starship. Well, theoretically it can. We haven't done it yet. Technically, it's a bit of a problem, but as far as the physics is concerned, if you had a black hole, you could power a starship and go to the stars with that. If you can power a starship with a black hole, why can't you power a sleigh and give it huge amounts of energy? The black hole would have to be tiny, not a huge star-sized thing. The black hole could be smaller than a grain of sand and would provide you with all the energy you need, no problem. but maybe Santa doesn't have access to a black hole. There's an alternative energy source which we're overlooking. It's the elephant in the room as to where all this energy might be accessible for Santa. What happens to all the mince pies? Even if you assume that not everybody leaves a mince pie for Santa, there's still a lot of them. And mince pies have mass, and we know from good old Einstein that mass can be converted to energy and vice versa. E equals mc squared. So if we know the mass of a mince pie, we can calculate how much energy in principle can be extracted from that mince pie. What if Santa has figured out a way of converting mince pies into energy, and then he uses the energy to do his feats of amazing things, getting round really fast, carrying 1 billion presents? For those of you who don't like maths, look away now, because we're going to calculate how much energy is available. A mince pie is 50 grams, and so E equals mc squared, that's mass of 50 grams multiplied by the speed of light squared. Speed of light is huge, 3 times 10 to the 8th, 300 million meters per second. So the square of that number is big. And that gives you an energy of 5 times 10 to the 15 joules. Joule is a unit of energy, and I'll come back to that in just a second. That's one mince pie. Let's assume that a few % of households leave a mince pie for Santa. Let's try and keep the numbers very convenient. So let's say 20 million mince pies during the night are left for Santa. That gives you a total of 20 million multiplied by the number we just calculated, 5 times 10 to the 15. That gives you a total of 10 to the power 23 joules. Now, physicists are used to using joules. You might think calories, but let's just stick with joules. But how much energy is 10 to the 23 joules? Let me convert it into something that we can perhaps relate to. Imagine a nuclear reactor like Sizewell B or something. That generates gigawatts of power. So over the course of a second, it generates a gigajoule. And let's imagine that Sizewell reactor is running every second of every day of every year for 1 million years. That is 10 to the 23 joules. That's how much energy Santa has available during the night. The equivalent of a nuclear power station running for 1 million years is available to Santa during the 36 hours of his exploits. Okay, right. How do you go about extracting energy from a mince pie? E equals mc squared tells you the exchange rate. How do you go about doing it? Well, one way of getting energy out of matter, it's being done all the time, is you take that amount of matter and you collide it with an equal amount of antimatter in the Large Mince Pie Collider at CERN. As long as you've got the antimatter equivalent of a mince pie, then you're sorted. But of course, the problem is, we've got 20 million mince pies, but we haven't got 20 million anti-mince pies. So unfortunately, that doesn't work. That's a shame, because that would be a very easy way of getting all of the energy out of the mince pies. There is an alternative. It's not quite as efficient, but there is a way of extracting a large amount of energy out of matter. And we see it happen, not so much on Earth, but when we look out into the universe, we find that there are relatively efficient ways of converting matter to energy. And efficient in this context means we can get 10% or 20% or 30% of the matter converted into energy. It's not 100%, but okay, given that how much energy is available in a mince pie, that's still quite a lot. How do we extract energy from matter, or how does the universe do it? Well, we see it happening by dropping it into a black hole. When matter falls into a black hole, enormous amounts of energy are released, and we see that for, in some cases, galaxies which have a supermassive black hole at their core. Stars are being eaten by those supermassive black holes and radiate huge amounts of energy. Those galaxies are called quasars, and we see them at enormous distances. Even though these galaxies are on the other side of the observable universe, we can still see them simply from the sheer amount of matter that's falling into those black holes. Now, it's probably not mince pies that's falling into those black holes, so we would have to do the calculation and say, right, we know from looking out into the universe, that's a very efficient way of converting matter to energy. If we did drop a mince pie into a black hole, how much energy could we get out? Surprisingly, I can't find any papers on this. I've looked through the literature. I cannot find anybody who's researching this topic. It seems like nobody is actually studying the concept of how efficient is it to drop a mince pie into a black hole. I'm fairly sure that it would be enough, but it's difficult to get the numbers. Okay, so he's not breaking any laws, and it needs a huge amount of energy, but he has a huge amount of energy available to him. But how would he actually do that? Because I don't quite know how he would do that, even though the rules say he can. I don't know how he would actually achieve that. How, for instance, does he manipulate quantum theory and apply it to himself? How does he distort space and time the way that large amounts of matter would do? Well, one thing to bear in mind is, well, who says he has to be human? So maybe he's able to do these things in a way we don't really understand. But remember, nobody's ever seen Santa. We assume he's a portly, jolly fellow with a white beard, etc. But maybe he's got green skin. All kids are asleep when Santa arrives, and adults don't tend to see him. Therefore, maybe it could be somebody along the lines of Yoda there. So, to return to the original question, is Santa compatible with the laws of physics, or if you prefer, just how many laws of physics does Santa break? I think the answer is none. So feel free to draw your own conclusions about the portly, jolly fellow with a white beard and the penchant for wearing red suits. Because regardless of your conclusion, for a second time this evening, I will wish you all a very Merry Christmas. Thank you.